Okay, let's get started. 굉장히 자주 보는 느낌이네요. 뭔가 Okay. All right. So let's get started. So last time, if you remember, we basically went over basic operations, organization and operations of a cache, and we also, covered how we can optimize software to be more like cache friendly, right? Because depending on how, even if you do the same thing, and even if you do the same amount of the work, depending on how you, arranging like memory accesses, the performance can vary widely, right? So that's basically caching behavior. So some versions of the code may be more cache friendly than the others, right? So we actually more specifically we talked about loop interchange. Basically we actually have nested loop. Index I, J, and K, and depending on how you change the order of indexing, the nest, change the order of like a loop nest, the performance can vary widely, right? And then the basic goal was we actually try to maximize the number of sequential access, right? So if you have like 3 arrays, we try to access this like array sequentially in like a row, like a, in the same row as much as possible. That's basically the optimization we did last time. Actually, that improves spatial locality of the code, right? So because, you only pay like one time cost of cache miss, and then for the next like n accesses, you actually get cache hits, right? So that actually gives you like a significant performance boost. So the next optimization we can think of is, how can we try to improve the temporal locality, right? So that and we in particular we introduced the a technique called blocking or tiling. So I'm going to introduce what the blocking is about. So here is like again the same like a matrix multiplication example. So it's a triple nested loop with like index I, J, and K. So if you want to calculate a specific like output element, let's say C. Let's say pen doesn't work. Sorry. C. Let's say X and Y. Then you actually sorry, it's I and J. Sorry, if you want to calculate the C, I, J, then you actually have to read the entire row of A of I, like K, multiplied by B of K, J. Right? So this is the how we calculate the like a single output element in array C, right? So if you actually analyze the caching behavior of this program, let's take a look like this. So let's say we now calculating the value of C, 0, and 0. Sorry for the poor writing because I used my finger. So we ordered new pen, so please wait. Please be patient. So in order to calculate this thing, we have to read the entire A of 0 and K, and we also have to read the entire B of K 0. Right? So that's the access pattern, right? In order to a single element in the output, we have to read the entire row and the entire column, right? That's what it needs. So here's the assumptions. We actually matrix elements are doubles. Each element basically takes 8 bytes, right? Because it's double precision, floating point, 754 in the standard. It takes like 8 byte to represent a single value. Cache block size 8 doubles. So you can it's like a 32 byte block, so can you actually pack like 8 doubles in a single cache block. We also assume this like cache size is much smaller than the dimension of the array, right? So and like let's say we actually do like a gigantic, like a big like array, big matrix, so that cache is relatively much smaller compared to the size of the matrix or array, right? So let's do some like cache miss analysis. First iteration, in order to calculate this like C of 0 and 0, how many cache misses we're going to have. So if you remember, this one is pretty nice pattern, right? But still, we actually have cache miss over like every it's actually we actually have like for this one actually we have like every cache miss it takes like every this one is cache miss rate 1, right? Because the second one, like if you have like n elements, we're gonna have n cache misses. But like a second one, because we can actually pack like a 8 doubles. Sorry, I made a mistake. It's actually 64 bytes, right? So cache block is 64 bytes instead of like a 32. I was wrong. So if you actually read a row, because we have cache miss at every 8 axes, right? Because we have cache miss and then followed by like a 7 hits. And we have cache miss followed by 7 hits and so on, right? Because single block actually can hold like 8 doubles. So in the first iteration in total, let's ignore like these cache miss just to like it's one-time cost, right? Because only one like miss. So if you only calculate like these two, because n is huge, like n is very large value. So in the first iteration, we're gonna end up having 9n over 8 misses in total. We just ignore like just single like one miss in the C. I mean this kind of tiny fraction. So and then at the end of like a first iteration, what blocks will be in the cache? Okay, so in this case, these last like 8 doubles will be placed in the cache, right? Because we actually do like read the entire row, and then this one will be in the cache, right? Because it's the last one we actually read from the memory. But what about this thing? So whenever we actually have a cache miss here, this actually shows very poor cache miss behavior, because even if you only need like this one element, the cache actually reads the entire block of like 8 doubles, right? So if you have a cache miss here, if you have a cache miss like here, let's say you have like you have one element. You have one element here, then you actually read like 8 doubles into the cache, right? So you actually end up having some like this like a square. I mean, these red boxes will be placed in the cache, right? So it's kind of waste, because you only need like this one like a double, but actually you read like 8 doubles, and the other 7 in the block will be wasted, pretty much, right? So what about second iteration? So now we calculate C of 0, 1. So it requires reading elements in array A, 0, K, and B, K, 1, right? So that's kind of the row and column we have to read to calculate this value, right? So let's do the same thing. Let's do the same analysis. Again, it takes like 9n over 8 misses to read like this like a row and column in A and B. And if you actually do it again and again for the entire like elements in the cache, so we actually have to calculate n square values for the output. And each iteration takes actually 9n over 8 misses. So the total number of cache misses to calculate the value of C, like array, is 9n over 8 times n squared, which is 9 over 8 times n cubed. Right? So everyone follows me so far? So that's the cache total number of cache misses we have to calculate the entire array of C. Okay? Actually, can you do better? So the answer is yes, because the point is here there is some waste, right? Because even if we load this like entire like a red box into the cache, we only use like a tiny fraction of the loaded like a cached value. Okay? So now we introduce the idea of blocking. So blocking is something like this. Now you actually divide this like entire array into like a smaller blocks. Okay? So now you actually have like a smaller blocks in it, and you calculate basically like multiply between these blocks. Okay? Because this block is relatively small, they can actually fit in the cache, right? This block is chosen to be chosen such that they can actually fit in the cache. Okay, so you read like a two like a small blocks, and then you do like a row and column like a multiply. So calculate the sum of the products for like using these like a small blocks, and then you add them up into the like array C, and then you repeat the process for all the blocks in the array. Okay, that's the basic idea. So in other words, or another way to think of it is, if you actually say, let's say you have to calculate this array of C, like you want to calculate the array of specific element, array, element C of I and J, right? So let's say you want to calculate a specific array element, value of a specific array element like this, right? Then what it takes, you actually need to read the entire row, entire column, and entire row from A and B respectively, right? In order to calculate like this. Of course, these row and columns are read from array A and B, not from C, right? But to like superimposing them, like you overlay them. In order to calculate this like one value, you actually have to read the entire like row and column, right? But if you actually want to calculate like a block of values, let's say now instead of like calculating a single value, let's say now you calculate like a small, block of values in C. Then you actually have to read like this, like a set of columns and set of rows, like this. Okay, so the ideal block, you calculate like this block of value at the same time by reading the entire like a set of rows and set of columns together. Okay, in that way we can actually exploit better temporal locality. Okay, that's the basic idea. So we actually calculate some range of values, like this block of values, instead of like a single value at a time. That's the basic idea of blocking. So here, as we show in this figure, we want to actually calculate like a certain like a block of value. Let's say block size is B by B. So if you want to calculate the this like a block of values in the output, you have to read like this array of blocks from A, and also you have to read this array of blocks from B. Okay. So the way it works is that in the first iteration, let's say now we actually have like further like an inner loop. Also, we actually change the increment by B instead of 1, right? So the outermost loop now actually, the distance is basically like a size of B. So in the next iteration, you actually move to the next plus B, and next iteration you go to like another like plus B, and inside like this loop, now we actually calculate this sum of product here. Okay. So in the first iteration, let's say initially I, J, K are 1, right? If I, J, K are 1, then we actually first, of course, this one is not quite, it's not really, actually we have to take the value from here. If the I, J, K was 1, then we first, read the value from here, like I, J, because, I, J, K, all like I, J, K are zeros, actually 0. So if you actually read the value from here, and we read the entire block from here, and we basically do the calculate the sum of the product, and we calculate the partial sum of this block in the first iteration of I, J, K. Okay, so in the next iteration, so everything is basically it's incremented by K. So now actually we actually load the entire there's like a second array. Let's say IJ actually move to the next array. So we actually this one is for like IJ 0. I and J are both 0. In the next iteration, I is still 0, but J is like a B. So now actually move to the next block here. So you actually move to the calculating this block in the next block, and then we load the value from the second block, the second block here, like second row, and we also calculate the value from the also get the value from this first row, block of row. So in that way we can actually calculate the partial sum up here. But of course we need to repeat the process for the entire blocks here. So that's actually how we can calculate the value. So again, I mean, if you want to calculate like a block of this value, you first calculate the sum of product for this sub-block, this block and this block, and 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 this block and this block. In this case, if you complete the, calculating the sum of products for all the 5 blocks, 5 pairs of blocks, then you can actually end up calculating the entire like block of value at the output. Okay, that's the basic idea. Okay, so if you actually do it this way, what the cache miss rate will look like. So again, we make the same assumption. Cache block, single cache block can take 8 doubles. And cache size C is much smaller than the array size. And also we assume that cache size B, block size B is chosen such that 3 blocks, because we actually calculate first, calculate like a sum of product for these 2 things to calculate this partial product for partial sum for this like output like a block. So we assume like at any given time, the 3 blocks can actually fit in the cache. Like a cache size is large enough to hold like these 3 blocks together. Okay, then what will be the cache miss rate here? So let's say in the first iteration, again, we calculate the partial sum for basically we do like a mini like a matrix multiply with like these 2 blocks. So in the first iteration, it takes like a b square over 8 misses per each block, right? Why? Because let's say we have like a block size b, then now actually we can actually read the value in this order, right? Within this like this like a block. Then eventually, we actually have cache miss at every 8 misses, right? So once you actually have like every 8 like memory element. So if you actually to let's say we have like b by b elements. If you have like a b by b elements, then the total like cache miss to get this block into the cache is b by b over 8, right? Because let's assume like a b is like a divisible by 8. B is some like a multiple of 8. If you make that assumption, the total number of misses to load the entire block into the cache is the total like a size of number of elements divided by 8, because we actually have like a 1 cache miss for every 8 like elements, right? So that's the reason why we actually have like a b square over 8 misses for like a loading like each block into the cache. And also we actually do this thing for n over 8b blocks, right? Because for like column, we actually have like n elements and each block size is b. So we actually repeat the process for like n over b blocks. And this one is like also like you have to pay the same cost for like a row and column, right? Because you have to, in order to like load, in order to process all these like rows, you actually have to pay like n over b times like that like a number, like b squared over 8, right? Because we have like an n over b blocks for this like row of like blocks and also for the column of the blocks. So if you multiply them too, this one is like a total number of blocks. This one is like total number of blocks. Total number of blocks to calculate like this the value of the single block at the output, right? So that's basically how many blocks we have to access, and if you multiply the number with like b squared over 8, then the total number would nb over 4. So here we assume the cache miss for C. C is basically this one it calls another like b squared over 8 cache misses. So if you want to really precise, actually you actually have one more here. It will be like, to be precise, it'll be 2n over b plus 1 times b squared over 8, because actually we have to pay the cache misses for this array C as well. But we actually we assume that this is much greater. I mean 2n over b is much greater than 1. Then we can simply omit like this term. So to be approximately, we can say it takes nb over 4 cache misses to calculate this block. Okay. So what the cache will look like? So afterward, once you actually finish executing the executing this like first iteration, the entire like a block of C will be placed in the cache. And also this last block will be in the cache. And also this last column will be in the cache. Like the last block in the column will be in the cache. Okay? So we actually make really like good use of this locality, right? Because no element is wasted. So in the previous like example, we in the column access we only like read like one element, but the other like 7 elements were wasted. But in this case, the entire block elements will be fully used. So there's no waste in a cache space. Okay, so that's where this like efficiency benefit actually comes from. So in the second iteration, we actually do the same thing. Sorry, actually, this figure shows a little bit. This one is a little bit of a mistake. So this like second block must be placed here actually, right? So the second block must be placed here. So now let's say now we actually calculate the value of this second like block. Then you actually have to read again. You have to read this like 5 blocks here, and also you have read like these 5 blocks here to actually compute the output value for like this block, right? So actually it does exactly the same thing. Again, the total number of cache misses, NB over 4, and if you actually repeat this process, then you actually have to do it for all the blocks in the output, right? So what are the total number of blocks here? So total number of blocks will be, because we actually have N over B blocks on each dimension, so the total number of blocks will be N over B square. So if you actually multiply this number by N over B square, then actually we end up getting like N square over 4B. That's the total number of cache misses in like a blocked code. Okay. So let's compare them. So this one is our second version, which is like a blocking, where the blocking is applied. And if there's no blocking, the total number of cache misses were, 9 over 8 times N cubed. If you actually apply blocking, then the total cache miss rate will be 1 over 4B times, N cubed. Okay? Then if you see this figure, like if you see this like numbers, then actually suggests the largest possible blocks will be desirable, because actually if you actually higher like value of a B, then actually we actually have fewer cache misses with blocking, right? That's actually true. But eventually, the block size is actually limited by, this constraint, because, we assume that now we assume all these like 3 blocks currently being worked on can be placed at the same time in the cache, right? So eventually, these like 3 blocks, the size of 3 blocks must be actually smaller than the size of the cache. Okay. So that constraint must be satisfied. So we cannot really, increase the size of block infinitely, right? There's some like a limitation because of like this constraint. Okay. So this one actually can show like a significant, like a very dynamic, like a significant, like dramatic difference. The reason is, the matrix multiplication actually has inherent temporal locality, right? Think about it. So, the input data, the input and output array like data size is like a 3n square, right? Because we actually have 3 arrays, C, A, B, right? 3 arrays, and each array takes like n square, right? So the array size is like 3n square, right? But the computation, because we actually have a triple nested loop, right? Because we actually do, if you think about the innermost like loop body, the add and multiply will be calculated like a n square times, n cube times, right? So that means there is like an inherent like temporal locality, because you actually have your input data size is in the order of n cube, n square, but the number of operations are in order of n cube, right? So that means every element must be somehow like reused at least like n times, order of n times, right? So that's basically temporal locality. Because let's say your data size is proportional to the n square, but your operation is proportional to n cube. Then there's like an order of n like a difference between the two. So that implies that because you take this operand solely from those arrays, that means every array element should be used like order over n times because there's like a difference. Okay, so if you really like make good use of this temporal locality, then you know, the one array element will be used like n times. Hopefully, when this one is in the cache. Okay, so that's basically, you know, best thing we can achieve. You know, but program actually has to be written and, you know, transformed properly to actually exploit this opportunity. Okay. So this summarizes, you know, caching part. You know, cache memory. We also, you know, talk about organization, operation, and also, you know, software optimization for caching. So any questions about, you know, this part? 뭐를 삼행제곱까지? 뭐를 내린다는 거죠? 뭐를 내리? 아, 캐시 미스 레이스요? 그렇죠. 사실은 정말로 템포럴 로컬리티를 완전히 100% 이용한다. 그죠? 왜냐하면 우리가 생각해 보세요. 아주 좋은 질문인데, 우리가 지금 이 프로그램을 실행할 때 필요로 하는 토탈 넘버 오브 메모리 액세스를 생각해 보세요. 그럼 토탈 넘버 오브 메모리 액세스는 n 큐브에 비례할 거 아니에요. 그죠? 왜냐하면 오퍼레이션 자체가 n 큐브 번 하는데 한 번 할 때마다 3개의 오퍼랜드가 필요하니까. 그죠? 실제로 얘가 메모리 액세스를 생각해 보면은 3n 큐브 번이 필요할 거 아니에요. 왜냐면 한 번 액세스 할 때마다 이게 A, B, C를 한 번씩 액세스한다고 치면 3n 큐브 번이 필요하겠죠. 근데 실제 메모리 액세스 해야 되는 그거 숫자는 그런데 그 중에 실제로 디스팅트한 엘리멘트의 수는 3n 스퀘어잖아요. 그럼 만약에 우리가 진짜 퍼펙트한 캐시가 있어가지고 얘는 한 번만 올라왔다 하면 절대로 안 내려간다. 한 번만 일단 캐시 위에 올라왔다 그러면은 절대로 안 내려가는 무한히 큰 캐시가 있다고 생각해보세요. 무한히 큰 캐시가 있으면은 그러면은 그게 아마 바운드가 되겠죠. 왜냐하면 한 번 정도는 한 번 이게 캐시가 올라올 때마다 한 번씩 그 페이를 처음에 한 번 올라오는 코스트는 페이를 해야 그나마도 스페셜 로컬리티로 어머타이즈 할 수 있으니까 사실은 3n 스퀘어가 아니라 거기에다가 8을 나눠요. 왜냐하면 올라올 때마다 8개씩 올라온다고 치면은 결국은 예를 들어서 마지막에는 그러니까 한 번 액세스 할 때마다 8개의 엘리먼트가 올라오고 한 번 올라온 엘리먼트는 절대 나가지 않는 캐시에서 절대 빠지지 않는다고 생각하면 캐시가 만약에 무한히 크다고 생각하면 그죠? 그런 무한히 큰 캐시가 있으면은 그거는 3n 스퀘어를 8로 나눈 것만큼만 액세스 실제로 바깥에서 그 메모리 액세스가 필요하겠죠. 그 캐시 밖에서 액세스는 그게 어떻게 보면은 캐시의 로어 바운드인데 그 캐시 액세스 개수의 로어 바운드인데 사실은 더 잘할 수도 있어요. 그거보다 더 잘할 수 있는 방법. How we can do better than the 3n square over 8 times of like a option memory accesses. We can actually do prefetching. I briefly mentioned prefetching. So if you know which data will be used like next time, you can actually put those blocks into the cache before that's being accessed, right? Then you don't really have to pay this like a compulsory misses because the block you need is already placed in your cache, right? Then theoretically you can actually reduce the cache miss rate to 0 because if you do like a perfect prefetching, so perfect prefetching means you actually know which block you're going to use in the next time. So you place this block into the cache before it's being accessed. So every memory access actually generates a cache head. Then cache miss rate will be 0. But that's in theory. If you do have like a perfect cache and perfect fetcher, then that may be true. But in realistically, what you say is true. So the total number like found in the number of like off-chip like a DRAM accesses can be some like a order of like a n cube. Probably you go 3n over 2 divided by if you have perfect like a large cache. Okay, any other questions? All right, so we have still a long way to go, so let's move on to the next topic. So now we change the gear to talk about the virtual memory. These like a virtual memory. So far, we actually talk about the caching behavior between CPU and main memory, right? But this virtual memory is about like a caching between main memory and disk. Okay, so we can actually basically apply the same principle of locality, and hierarchical organization and locality in, organizing this like virtual memory. So in virtual memory, this main memory is work like a cache. So now main memory becomes cache, and disk is the memory. So it's now we actually do the same thing, pretty much the same like principle, apply the same principle, but in the like one level lower. So instead of like between like a CPU and main memory, now we apply the same principle between main memory and disk. Okay, that's like what like a virtual memory is about. So maybe like as like a motivating example, how does this work? So in your computer, your computer actually doing like a multitasking, right? You actually run like a multiple different program, or if you have taken like operating system class, you call it like a process. You actually run like a multiple processes at the same time, right? Because that's like multitasking. So if you basically do like a web browsing at the same time, you do word processing, also you're playing like a music, all these things you actually do the same at the same time, right? So there are like a multiple like a programs actually running at the same time, or to be precise, multiple processes actually running at the same time. So what is process? It'll be more precisely defined in the operating system, but at the moment you can think of it as like a different like context. I mean different like program or different like applications. Okay. So let's say we have like a multiple processes or programs at the same time. So then how they actually share the memory? Because memory is a shared resource among all these like programs you're running at the same time, right? So if you actually load, like if you actually start your program is always loaded into the same position in memory. So in this specific example, this is like a 400000. This one is the where your like a main function is actually placed if you write the program in C. Okay, so whenever you actually click, whenever you click like application and launch or your program, your program is always loaded and in the address like a 400000 at the fixed like a location. And also you're like a stack. We also talk about stack, right? Your stack always starts at the same like a location, regardless of the program. Also, there's like other like a region, like a data region. This data region is for like a static data. If you actually if your program actually has some like constant value, such as hello world, or some like constant number 3, all these like constants, or if you have like global or static variables, those like data is actually placed here. So my point is, regardless of the program, they actually have the same memory layout. I mean, their program code always starts at like a predetermined location, like a 40000. Your stack always starts from 7FFFFFF. You're like heap space always starts from some location and so on. Okay, then how they actually can work together? Because we only have like one like single piece of memory, like a physical memory. But actually, what happens if you do two programs that tries to run at the same time? How they can actually share the memory? Because I want to run program A here, I want to run program B here, and they actually occupy the same memory address, right? Starting from the same memory address, they actually they make some contention. Okay, so how we can solve the problem? How can run like multiple programs at the same time without conflicting with each other? That's actually the question you want to answer in this lecture. It's about the solution is like virtual memory. So I'm going to talk about what is virtual memory, how this works. So first of all, let me introduce the concept of address space. Okay. So in like each program in virtual memory system, in each program actually has its own address space. Okay. And this address space is different from the physical like a DRAM address space. So, but there's like some mappings, but each like a program has its own like a private address space, and they can be, they actually, share the like a physical memory using like a virtual memory system. So let me explain the concept. So here, let's say, in like early like a 1950s and like old machines, there's no multitasking. There's only one program can run at the same time. There's only one program run any given time, and that program actually takes like all the resource in the computer. So there's no multitasking. Okay, so in that case, you can use like a physical address that once you actually have like a load and store instruction, or you actually read like a fetch instruction from memory, you can actually use what is called physical address. So physical address is the actual like a DRAM like address in the DRAM. Okay, just because there's like you have like a main memory. Let's say your memory actually has like M byte. You have M byte address space. Then you actually have like M different like locations you can actually access. So this one is like a physical. This is called like a physical address space because that there's like a one-to-one correspondence between this like an address and actual like a physical location in DRAM, right? So this one is still used today in simple systems like an embedded microcontroller, which only does like which only runs like one program throughout its lifetime, like cars, elevators, and these are picture frames. They actually it's like embedded. In this case, they only run like one program. It's not really programmable. It's programmable, but they only run like one application, like one program throughout its lifetime. Then it's okay to use a physical memory. But if you actually use like a virtual addressing, let's say virtual memory system, then CPU actually generate an address which is like a virtual, 가상의 address라는 거죠. It's not physical. Okay, so once you actually generate like a memory request using virtual address, then there is like a memory management unit in the middle, MMU. MMU is memory management unit. So memory management unit is responsible for translating this virtual address to physical address. Okay, so let's say I access special like address, like certain address called like a 4100. Let's say 4100 is the address I want to access. Then this MMU, it actually maintains a table inside it, so that it actually make a translation from virtual address to physical address. This like mapping information can be managed by this MMU, memory management unit. So if MMU takes the request with address 4100, this one will be translated into physical address 4. So actually the data is actually read from like this location and come back to memory. Okay, so this one is example of a virtual addressing, and this like virtual addressing is used in modern servers, laptops, and smartphones, all the computing devices you can think of today. This is a very standard feature in today's computing system. So let me precise how we can define the address space. So the linear address space means like an ordered set of contiguous non-negative integer addresses. Okay, so linear address is basically 0 from some like maximum number, maybe like a 48-bit address space, or like 40-bit address space. Then actually you have like ordered set of starting from 0, 1, 2, 3, up to like 2 to the power of 40. That's called like a linear address space. And there are two distinct like a linear address space. The first one is virtual address space. So let's say you have like a virtual address space. Then we actually have like n virtual addresses here from 0 to n-1. And there's a physical address whose size may be different from like virtual address space. In this case, we have like m different like physical addresses, or we can access like m different like physical like m different like bytes physically. So this like a physical address space is actually to first order. This one actually has the same. You actually have like a valid like address space whose size is the same as your size of your DRAM. Okay, So if let's say your computer actually has like 8 gigabyte DRAM on your computer, then this like, physical address space will be somewhere between 0 through 8 gigabyte. 8 gigabyte is 2 to the power of like a 33, right? If you actually have, your computer actually has like 8 gigabyte memory, then the physical address space will be 0 from, 2 to the power of 33 minus 1. But this virtual address can be arbitrary. I mean, it can be like arbitrarily large. But the typical like a virtual address space is somewhere between maybe 28, 48 bits. It's kind of a standard, I mean, in Intel architecture, x86 architecture. So, but the point is, this like a virtual address space can be, usually in general, is different from the physical address space. Okay? So let's do some like a thought experiment. So let's have a, like a, thought experiment. You know what is malloc, right? Memory allocation, like heap space memory allocator, right? malloc. 알죠, malloc. 그죠? 그러면은 when you execute malloc, let's say you have like a physical memory of like 8 gigabyte. Okay? Physical memory. And let's say you malloc like a 16 gigabyte. Okay? So would this work or crash? Would this just work? Let's say you malloc like some like array, like an integer, like array A, and then you access this array like with very high number. Okay? Let's say you assign the number to the array. Okay? Then would this program just work or will it die? Okay. Don't go ahead too far. He's exactly right. So this actually works. Okay? I'm joking. I'm encouraging you to go ahead. So yeah, this one is basically, this one actually works. Why? So you can, even if your physical memory is only like 8 gigabyte, you are allowed to, allocate like a 16 gigabyte memory space. Okay? So the natural question arises, where all these like elements will go? Okay? So if you actually have like a 16 gigabyte like array and your physical memory size is just 8 gigabyte, then what's happening here? And this program just works. So in maximum, your memory can hold up to like 8 gigabyte of data, array data, right? So where is the other like 8 gigabyte of data go? Where? Any guess? 어디로 갈까요? 나머지 16GB의 어레이를 잡았는데 내 피지컬 메모리는 8GB밖에 없어요. 그러니까 물리적인 진짜 DRAM 메모리 8GB밖에 없는데 내가 어레이 멜록 해가지고 16GB 잡았는데 다 데이터를 다 써요. 그러면 나머지 8GB는 어디로 갔을까요? Where is the other like 8GB go of data? Disk. 오케이? 그러니까 8GB, 16GB를 잡아도 그 중에 일부는 DRAM에 올라와 있고 나머지는 디스크에 저장되어 있는 거죠. Okay? And if you actually request the exact like an element that is currently in the disk, then what is called like a swapping is happening. So swap is basically it's like a cache. So you actually read this like block into the main memory and then kick out evict to like one of the existing like things to the disk. Okay? In that way, you can actually using like a virtual. This is one benefit of virtual address space. Because if you actually have like a physical addressing, your like address range, the maximum the elements you can access is limited by the physical address size, physical like DRAM size, right? But if you actually have like a virtual address space, generally virtual address space is much larger than the size of DRAM. So it allows you to work on like a much larger set of data, large size data than what your physical memory can hold. Okay, so that's like another like benefit of virtual space. So what's the virtual memory? Why we need virtual memory? There are three like reasons. The first one is we use main memory efficiently because we want to do support sharing. Because now there are like multiple like programs running at the same time, and the memory, physical memory, and disk is a shared resource. So we actually make use. We want to make use of this like main memory efficiently. The idea is use this main memory DRAM as a cache for parts of this virtual address space. So as I said, your virtual address space can be a lot larger than what you can hold in the physical memory. So this physical memory is actually used as a cache for the entire like, virtual address space you're using. Okay? And also, secondly, it actually simplifies memory management because each actually process get the same uniform, like a linear address space, so that now every time you actually your operating system, whenever you launch a new program, operating system always load this like a program code in the same like address, and also initialize this like a stack in the same address, regardless of how this actually memory is being used, right? So if you actually use like a physical addressing, then this like a starting address to your program and your data will be placed, after considering how this memory is being used currently, right? Because maybe this address 4000 is currently occupied by another program, then you actually have to place your program to the different like a location and so on. This is like all headache, right? But if you actually provide like a virtual address, then all this program actually starts at the same like address, and the stack space always starts at the same address and so on. So you can actually have the physical layout of the memory space for all the programs running at the same time, right? Without crashing with each other. Okay, I'm gonna tell you more details about how it works in this thing in like a later slide. And finally, it allows you to isolate address spaces. Isolation, right? Let's say your program has using like physical addressing, right? Then you can actually using like this like a physical address pointer, you can access arbitrary location in the memory, right? But maybe so some of the memory location actually have some like a sensitive like information. Let's say privileged information. Okay. If you actually use like a physical addressing, it'll become the nightmare of like a security, because any program running in your program can access any location in your memory. So you can actually corrupt your program, or maybe extract some like a sensitive information from the other program, and so on, right? So we actually want to provide isolation and protection between different programs, so that a program can only access those region of like memory that program is allowed to access. Okay. So also this without isolation, the debugging will be nightmare. The program debugging will be nightmare, because let's say any program can access like any location in your system, in your memory. Then let's say there's a buggy program. There's a program with a bug. You can corrupt like arbitrary location of the other program, right? Then the other program actually dies without knowing the reason, without good reason, because the other buggy program can corrupt the data of the another program, right? So that's basically the benefits of using like virtual memory. So that's the reason why this virtual memory is kind of the very like a standard feature for all the computing systems today. So let's go over these like three like benefits of using VM, virtual memory one by one. So let's start with VM as a tool for caching. Okay. So the first point is VM is virtual memory actually provides allows you to use this main memory more efficiently. So conceptually, virtual memory is an array of n contiguous bytes stored on disk. Okay. So let's say you have like a virtual disk space, and in your program, by default, let's say all these like program data in your virtual disk space are actually stored in disk as a file. Okay, and the contents of the array on disk are selectively cached in the physical memory, or DRAM cache, or DRAM as cache. Okay, so in this case, so you can actually define arbitrarily large like a structure on your like a virtual disk space, which is stored in disk by default, and then you selectively place blocks in this like a memory space into the physical memory. So in other words, this like you use this like a DRAM as cache for disk. Okay, so this figure actually shows an example. Let's say you have some like virtual disk space here. So some of these blocks are unallocated, some of the blocks are cached in the memory, and some of them are allocated but not cached, meaning that it's still in the disk, or some like other space, like some block is not allocated, like some are cached in memory, and so on, right? So in this way, we can actually use like arbitrary large size of data, as long as this virtual address space permits. But we can only selectively cache this like hot blocks or pages. By the way, page is is a block in this context. So we actually selectively selectively like allocate these like pages, like hot pages, into the physical memory, which actually provide much faster access time. So this one is a slow disk, and this is fast memory. And by default, we actually place all these like pages or blocks in the disk, and selectively place them into the physical memory. Okay, so virtual pages are stored. Pages are, as I said, pages are blocks in this context. Block, cache line, cache block. That's the unit of like transferring from like a lower level layer and upper level layer. In the cache, we call it either like line or block, cache line or cache block, right? And page is the name for this like a unit of transfer between this disk and main memory. Okay, so these blocks are called pages, and let's say the page size is that's our notation. So P is the the page size. Typically, the page size is like a 4 kilobyte to 8 kilobyte. That's a typical number. So whenever you actually have cache miss, in this case, this is called a page fault. Whenever the data you're looking for is currently not in the memory, then actually that's like called a page fault. If page fault happens, you allocate the entire like page into the memory, and the page size is like a 4 to 8 kilobytes. That's a typical number. So how we can organize this DRAM as cache? So this DRAM cache, this paging system is organized. The organization is driven by the enormous miss penalty, because whenever you have a cache miss, or in this case, cache miss is a page fault. This cache miss is called like a page fault. If page fault happens, you actually have to load this page, request the page from disk to memory, like a DRAM. And DRAM is about like a 10 times slower than SRAM, but this case is about like a 10,000 times slower than DRAM. Okay, this one is like a the performance gap between processor like a CPU cache and main memory, but the gap is much larger between this like a main memory and disk, like 10,000 times like a slower than DRAM. So as a consequence, this DRAM cache actually uses much larger like a page size, or page and block is the same. The page size is much larger, typically like a 4 kilobyte, or sometimes even like they support like a huge page, like a 4 megabyte, or even like a 1 gigabyte page is supported in today's machine. And also fully associative structure, because fully, if you remember, if you have like a larger or greater associativity, then generally cache miss rate actually goes down, right? So the two-way set associative cache actually performs better than direct map cache, and four-way is actually performs better than two-way, and so on. If you actually increase the associativity, that actually reduce the cache miss rate at the cost of hardware, right? Because we actually have to pay the cost of this comparator, all this extra logic. But because this like cache miss cost is too big, this like in this context, we want to avoid this cache miss at all cost. We just want to avoid it as much as possible. So we actually adopt like a fully associative like a structure. So any virtual page can be placed in any physical page. There's no restriction of where it can go. So it's fully associative. So, but actually it requires like a large mapping information. So unlike these cache memories, we actually have like a big, like a gigantic, like a table, which actually tracks which virtual page is currently mapped to which physical page, or currently in the disk, or is unallocated. You actually have the comprehensive like a table that actually maps every single page in your virtual disk space. And also it employs highly sophisticated, expensive replacement algorithm. Instead of like a simple like a FIFO, first in, first out, or random replacement, instead of that, it actually employs very sophisticated page like replacement algorithm to minimize cache miss rate. And also it actually does like a write back instead of like write through, because it takes a long time to write into the disk, right? So it actually use like a write back scheme. So it actually buffer this write as much as possible inside the memory, and then write to the like a disk at once. I mean in burst. Okay, that's basically concept is a cache organization. Okay, so as I said, if you actually really want to have like a fully associative structure for this like organizing this caching system, so we need to have like a very table which actually tracks where each of these like a virtual pages is actually mapped to. Okay, so that table is called page table. So page table is an array of page table entries, or PTEs. So array of PTEs that maps virtual pages to physical pages. And this one actually shows an example of physical, page table. Say, this table actually this table itself is sitting in the DRAM. I mean, so typically, it's sitting in the memory. So let's say we have like small like page table with 8 like elements, like PT0 to PT7. So in this case, the first like VP0, like virtual page 0, is currently not allocated. This memory space not being used. I mean, by the program, and maybe the VP1, the first page, is currently mapped to like DRAM. Currently is cached. So like this. So in this like address space, we only have like, let's say we have very tiny like a virtual address space, which only have like 8 pages. Okay, so we have like 8 pages here. Then among these like 8 pages, 4 pages are currently cached in the DRAM, shown in this like blue, and 2 like pages are currently in like disk. Okay. And the other 2 pages are not being used. They are not being used. They are unallocated. Okay. So even if like you have like a huge like address space, at any given time, typically you only use use only very small set of this address space. Okay. So that's the reason why some of these actually pages are currently placed in the DRAM, and some others are they are like not being accessed for a while. So they are currently placed in the disk, and the other 2 pages are currently unallocated. Unallocated is not being used at all. Okay. And this like a page table is per process kernel data structure in DRAM. So whenever you actually start a new program, a new page table is created by the operating system, so that the operating system actually initializes this like page table, and whenever you allocate like a new like space, like using like a malloc, right? Malloc is kind of you request some original address space, right? Then now that address space will be allocated. That virtual address space will be allocated to the program, so it's valid to use like this range of this memory, and that is actually managed by the operating system. The mapping between this like a virtual address space and like physical address, physical pages are mapping is actually managed by the operating system and hardware. So there's notion of page hit. You request like a specific like location in the memory using virtual memory, like virtual memory, virtual address. Then let's say the reference to the virtual memory word that is currently in the physical memory, then that is called page hit. Okay, the page hit is a cache hit. So it's like the case. In this case, let's say you request like a specific, you want to access like a specific memory location. Of course, your program only sees the virtual address, because all these user level like a program like pointers are basically virtual address pointer. So you access like a specific memory location. Let's say the address like a 4100. Let's say you want to access like a specific memory location, and that like whenever this memory request comes in, you have to first look up this page table. Okay, so if you access the page table, you can figure out where this page is currently placed. So let's say the page you want to access is currently, let's say this one is the page you want to access. Then this one is currently in the cache, right? In the DRAM. What I mean by cache is like a DRAM here. So in this context, so currently in the DRAM, then this is called page head, right? Because the data you are trying to access is currently in DRAM. This is called page head. Also, virtual address is coming in. Then you first look up the page table to locate where this request page is currently located. And let's say you request like this page, you actually request this page, then you know that now you figure out this page being in like a DRAM. Now you can access. And also you can do like, there's like a case of page fault. So page fault means reference to the virtual memory word that is not currently in physical memory. So it'll be either like disk, probably in the disk. So let's say there's again, like you request virtual address, but this valid bit is 0, meaning that this page is currently in the disk, not in the cache. Okay, it's a cache miss. So if you have a cache miss, then what you have to do is first you have to evict because it's a cache. DRAM, this one is like a cache, right? So because you have requested a page that is currently in the disk, you have to first evict, like kick out one of the existing pages in the DRAM, right? You have to kick out one of the existing page, and we select a victim. So it's like a cache. It's like a replacement policy in the cache. So we also in the same way we select a victim to evict. So in this case, let's say this virtual page 4 is the victim. Then we kick it out and place this like a requested like page into the DRAM. Okay, and then we retry the access. Then now we can actually get the correct like value from this DRAM. So it's like exactly the same idea, because this like a virtual memory, like disk serves as like a main memory, and this like a physical memory, like a DRAM, serves as a cache. And the size of the block is page. And in order to actually find the location of the physical page, whether it's going to page hit or page miss, page fault, we actually have to look it up. It's like a table, which is called like a page table. Okay. So offending instruction, if there's page fault, the offending instruction is restarted. Now we retry the instruction. Then now in the second try, we get like a page hit, and now we can access, get the value from this memory location. And the key point here is that we wait until the miss to copy the page into a DRAM, which is known as demand paging. So demand paging is, when we first allocate like a memory, let's say you do like a malloc, you first allocate memory, then it just allocates virtual address space, but not physical like memory. So whenever you actually try to access this memory location, at that point now actually allocate like a new like a physical address space using this like a page fault mechanism, and this mechanism called demand paging. Okay. So it's like a page is like allocated. Physical page is allocated only when it was requested by the program. So that's the reason why it's called demand paging. Any questions about so far? Any question about what I covered so far? Virtual memory, how this like a page table and DRAM cache actually works. Any questions about what I covered so far? All right. So let me move on. So let's say now we allocate a new page. In the previous example, this like a page, like a virtual page, is currently null, meaning that it's unallocated. Okay. So if you actually start your program, your virtual address space is huge. Like virtual address space, like a 48-byte address space. 48 byte is like how many? 256 petabyte. Whenever you launch a program, your program is given like a 256 petabyte memory space. So you only use very small, tiny fraction of the entire like virtual address space, right? So most of these like memory spaces are unallocated. And whenever you execute a malloc or BRK, like block allocation, system call, then you now at that point you allocate this like a virtual address space to the program. Okay, so so if you want to, let's say you want to allocate like this like a location, like by like a malloc or some like system call. Let's say now you want to use this memory space as well. Then now this one is allocated and go allocated on a page in the disk as well initially. So now we allocate a new page like a virtual page 5 of a virtual memory, and we've created a mapping between this like a VP5 and this like a disk page in the disk. Of course, after that, if you actually request like a certain like a value in this page, then again, it will cause a page fault, and then now this like a VP5 will be loaded into physical memory, right? And then you retry the instruction, and then now you can read the value from there. So if you see, this virtual memory seems to be terribly inefficient, but this actually works. Because what's the inefficiency here? Because whenever you have to access the memory, if you actually use physical address, then you can go directly to the DRAM because you have physical address, right? But if you actually have like a virtual address space, whenever you need to access the memory, you have to first go to the table. I mean, it's like a page table, right? And then you find the mapping, to find the correct like a physical address, and then you can access the physical memory, right? So this one actually looks very terribly efficient, right? Because every memory access actually has to go through the address translation of the page table, right? But it actually works very well because of the locality. So any given point in time, the programs tend to access a set of active virtual pages called working set. That means, let's say even if your like a program actually use a lot of memory, so but any given time, any given phase of a program, you only use very small like a portion of this like address space. That portion is called working set. Okay, so program actually with better temporal locality will actually have smaller working sets. So if working set size is smaller than memory, like physical memory size, then actually we can achieve good performance because most of the memory requests we are doing will be found in the main memory, and the page fault rate is page fault rate is very low because all the data we are looking for is in the main memory. But if the working set size is greater than main memory size, then we're gonna have a lot of thrashing. So pages are swapped in and out between disk and main memory. So that actually causes a lot of like waste, memory traffic plus some like performance like a degradation if this working set size is greater than memory size. Okay. So that's how this VM works as caching. For caching, because now in the previous section we talked about this using DRAM as a cache for disk, and using this page table, we actually maintain the mapping between for any like physical like a virtual page we in our program. There's a mapping either to the like a physical memory or disk or unallocated. It's not allocated, right? The second benefit of using virtual memory is we can actually it actually simplifies memory management. So let's say now we have two like a program running at the same time, like two processes, virtual address space for process 1 and virtual address space for process 2. These two programs are running at the same time, you're sharing the memory. So you can view memory as a simple like a linear array, and this is like a mapping function. There's like a page table. There's page table for each of this for each process. And there's mapping between this virtual page to physical page like this, and this one is mapped to here, and this VP1 is mapped to this this physical page 6, and second VP2 VP1 goes to PP8, physical page 8, VP2 actually goes to physical page 6, and in this way it makes it easier to share the memory because by manipulating this like a page table, we can make this virtual page to point to arbitrary physical page. Okay, so from the process's perspective, this process can view this memory as simple like a linear address space, which is owned by itself because it has an illusion of entire memory space is owned by myself, right? So this kind of gives you an illusion of simple like a linear array, and it also make it easier to share the page. Sometimes like two programs or two processes, they actually need to communicate with each other, and in that case they actually have like a shared page, or maybe they may actually have some like shared data. Let's say like a shared library, like a DLL, like a dynamic link library, or SO file, like that's shared object. Then instead of like having this having like multiple copies of the same code, you can actually have only one version of the code, and the two processes actually point to the same physical page. So in that sense, in that way, we can actually make it easy to share page between two processes or programs. And also, like, it simplifies memory allocation because each virtual page can be mapped to any physical page, and virtual page can be stored in different physical pages different times. It gives you a lot of flexibility. So even if like a specific like a memory location physical page is being used by another program, you can still use the same like a virtual page, but only you have like a different mapping to the different like a physical page. So it gives you a lot of flexibility, and basically you can allocate any like free pages in DRAM to like any like a process. And also as I said, sharing code and data among processes become easier using this like a page table, because now we can map like a multiple virtual pages to the same physical page. Also, simplifying linking and loading. So I already explained this part a little bit because all these programs now actually have the same virtual address layout. For example, program code always starts at address 400000. The stack space always starts at 7FFFFFF. So you don't really have to worry about where this program actually where to place each data, regardless of the usage of memory from other program. So each program actually has similar virtual address space, and code, data, heap always starts at the same addresses. And it makes it easier to loading the program because regardless of the program, this initial like a program loading process is exactly the same because of thanks to the same memory layout. You can actually do the same thing for regardless of the program contents. So execve, actually this one actually system call that execute the program. So you actually launch a new program. This like a system call allocates virtual pages for text like your program code and data sections, and create like a page table entry marked as invalid. And because this is initially this like a program code and data is currently sitting in like a disk. And by demand paging, those like a program page and this like your data page is selectively loaded into physical memory using like a standard like a demand paging mechanism, which I introduced in the previous section. Finally, virtual memory as a tool for memory protection. So as I said, we can actually extend the page table entry with permission bits. Okay, the permission bits include maybe like this supervisor mode, read, write, executable. So maybe you can actually have like a designated like a protection flag. So in this case, let's say this one is you cannot read write to this page, but let's say you try to write to this like a page VP0, then the hardware actually checks whether any violation of this like a permission. So if you try to write to like a read-only page, then the system actually generates a trap or exception. So the operating system actually catch the exception, right? It shows an error message like you try to write to the read-only page, dies or something like that. So so MMU, memory management unit, checks like these bits on each process. Also there's like executable exec bit, so that if you actually try to jump into the like non-executable like a page, then it also generates a trap to actually stop your program, right? So this one actually provides you. This one is very valuable to protect your program and others from like misbehaving, misbehaving programs. Okay. All right. So actually, the time is up. So I'm gonna stop here, and I'm gonna go over this address translation next time. 네.